that works. Thanks, Carl. Well, thanks very much for the invitation. It's great to be here. I think I visited here for bring it up a little. Visited here very briefly for maybe more than 30 years ago at one point to visit Bob. And what Bob didn't tell you was that not only did I follow him as a graduate student, but I tried to do the same experiment, which was quite a challenge. I actually think I succeeded and maybe did it a little bit better, which was the goal, but got pretty much the same answer. And many people have tried to repeat that experiment since, and I don't know of anyone who's been very good people, actually. I think at Argonne they might be trying. Anyway, I think Carl knew because that it couldn't be improved, so he went and did something else, which was fine. Anyway, it's a great pleasure to be here. I want to tell you about what's going on presently and what we think will happen in the future at Jefferson Lab. So the outline is to give you a little introduction and science background, sort of why the laboratory exists and what the main focus of the scientific program is, and then tell you a little about the facility. And we're actually presently upgrading our main accelerator from a 6 GeV accelerator to a 12 GeV accelerator. And I'll tell you about some recent highlights and the future physics program that we expect to do with this 12 GeV machine. And we think that our future beyond that involves an electron-ion collider project that our version is called the MEIC, Medium Energy Electron Ion Collider. And I'll tell you what's going on with that and what we plan to do, and then give you a brief outlook. So I like to start with this slide because really Jefferson Lab is very well connected to lots of areas of nuclear physics and beyond, and I try to emphasize that at the beginning. So this is kind of a schematic of our accelerator, and we'll talk about that later. The traditional subject that JLab is mostly known for is the structure of hadrons, which you can study with precision electron beams very well, and we will continue to do that. The issue of how quarks are confined in hadrons is still not completely understood and is something that one can study in new ways with the upgraded facility that I'll mention to you. In addition, everyone, especially people who work on STAR, know that this is a picture from a heavy ion collision at the RIC facility at Brookhaven. And we certainly don't make quark gluon plasma with our electron beam. But I remind you that even at RIC, where you might make a quark gluon plasma that has a very dense medium with many quarks and gluons in it, that what they observe are actual physical hadrons in the end, and that those quarks have to emerge from the underlying reaction as actual physical hadrons. And the process by which quarks hadronize into hadrons is something we can also study in more precisely controlled experiments using electron beams. Less well known is our connection to the field of nuclear structure, which is something that people work a lot here on. There are many connections associated with the underlying fundamental nucleon-nucleon interaction, short-range correlations, and so forth that we can study. I'm going to highlight one particularly interesting one where we can actually study the neutron skin thickness in a heavy nucleus like lead-208. Fundamental forces and symmetries is an area of increasing activity at the laboratory. It's a really growing part of the program, and it's becoming a very substantial part of the program, and we're very excited about that. So I'll actually spend some time on various aspects of that program. Theory and computation, I'll touch on this occasionally. Of course, it relates to the structure of hadrons and all these QCD topics that are on this slide, but also areas of nuclear structure and supporting calculations for our fundamental symmetries experiments. And much of it, we have a lattice group that has been very successful at using graphical processor units for lattice QCD calculations. Medical imaging is an area where, in support of the detectors for nuclear physics at the lab, we have a group that has branched out successfully into medical imaging. They've actually spun off a company that has marketing a new higher resolution, higher sensitivity mammography system. And this is also the lab has a very strong history of accelerator science and technology. In fact, this is the largest installation of superconducting radio frequency cavities for an accelerator in the world, even to this day. And the lab is a world leader in the development of new technology associated with that technique. So let's kind of review how we got to building this lab. So I'll remind you that in the 1960s there was a dramatic discovery of quarks in what's known as deep inelastic electron scattering at SLAC. And they performed experiments. These three gentlemen won Nobel Prize many years later in 1990. But the experiment was to basically scatter electrons, detect only the electron. You can measure the energy lost and the momentum transfer in the process and infer information about the structure of the object that you hit, which in that case was a nucleon. And this is a subject that's been developed for many years. But shortly after that discovery, of course, the theorists developed the theory of quantum chromodynamics in analogous to QED. And so here's the typical Feynman diagram for exchanging a photon in QED. And of course, if we do elastic scattering from a proton with an electron, this is the diagram. But inside of the nucleon, the quarks interact by exchanging a gluon. And all of these objects have something called color charge. And what's different about this system is that the photons that are exchanged in QED have no electric charge, whereas the gluons exchanged in QCD do have color charge. And so the gluons have self-interaction diagrams, makes the theory much more challenging to calculate with. And so that's why, to this day, the actual structure of objects governed by quantum chromodynamics is not fully understood and cannot be calculated from first principles yet. So coming back to deep inelastic scattering, which was a big part of the story, again, here's this Feynman diagram exchanging a photon. It's very easy to write down the complete cross-section for such a process. This is for unpolarized scattering. That involves just two structure functions, W2 and W1. And out front is a simple formula that basically is the Mott formula. It's just a relativistic analog of the Rutherford scattering formula. And what was realized in deep inelastic electron scattering from the SLAC experiments is that if you measure W2 and you multiply by the energy lost by the electron, K minus K prime, you get a function that's called F2. That's a function only of the ratio of kinematic variables x, q squared over 2m k minus k prime. And this variable x, sometimes known as Bjorkane x, is interpreted as the momentum fraction of the partons, the objects that make up the proton. And if you can, in such a model, you can write this F2 of x as a sum over the charges. This is the electric charges of those partons squared. So this would be the 2/3 or minus 1/3 squared for the quarks times x times a momentum distribution known as the parton distribution function Fi of x. And one finds that this expression is true, roughly independent of the q squared that you use in the process. And this is the property known as scaling, and is an indication that the actual particles that you scattered from in this model are point constituents with no internal structure themselves. And so this shows this sort of simple cartoon picture that we have for a model for this kind of parton distribution. If you just scattered from a charge, then x would be the momentum fraction, which would be all of the momentum would be 1, it's the total fraction of the momentum, and all of the strength would be at x equals 1. If you had 3 point particles that were stationary, you would have all the strength at 1/3, which is each having 1/3 of the total momentum. And if the 3 quarks were interacting by exchanging gluons, so they were jiggling around, there would be a Doppler shift effect, so you would see a broadening of that distribution, still peaked around roughly 1/3. And if those gluons could radiate other particles and create quark-antiquark pairs, as really happens in a more complicated case like this, which really happens in the nucleon, there would be a soft tail or a soft part of this distribution where the Q-bar pairs that are made from splitting this 1/3 into smaller momentum fractions fill in this region below 1/3. And this is what one expects to get. In addition, as you change the Q-squared, it was realized that the SLAC experiments were done in a fairly narrow range of Q-square. And if you go over a much broader range of Q-square, you find that this scaling is not exact, and that actually there is a logarithmic dependence on the momentum transfer of these functions. And that tells you about the gluon distribution that is in this system. And so we actually know quite a bit about these distributions as a result of all of these measurements over a very wide range of momentum transfers, including measurements with neutrinos and so forth, that also can give us information on the flavor structure of the internal parton distributions in the nucleon. And so this shows the kind of modern picture we have, and this is from real fits to global fits to data. And so there are bands that indicate the extent of our knowledge based on these global fits. And you can see the valence quark distributions where you have up quarks and down quarks. And you can see a proton has the 2 up quarks and 1 down quark. And you can see the quark and antiquark. And there is this gluon distribution, which is really astounding in that this red curve is divided by 10. So it's actually 10 times higher on this graph. And to make it fit on the graph, it's divided by 10. And you can see that if you get to low x, where the valence quarks no longer are important, that the dynamics is completely driven by all of these gluons. And that the antiquarks represent kind of a secondary feature of all these gluons, as the gluons can make quark-antiquark pairs. There's an interesting region in between where the anti-down quarks exceed the anti-up quarks. And this is seen in something called Drell-Yan scattering. That's actually a very interesting non-perturbative effect, but I'm not going to have time to talk about that today. But this is just to give you an idea that we actually have a lot of information about these parton distribution functions, much more so than we had from the early experiments at SLAC. And we'll come back to that. So the modern view of the proton is it's an extended object, has a radius of almost a Fermi. The quarks are charged, the gluons are electrically neutral. There are quark-antiquark pairs that come from the gluons, and that there is spin and orbital angular momentum in all of these constituents. One of the things we're trying to do is understand how that is divided up. And an important point is that if you take the quark masses inside of a proton and add them up, you get a very small fraction of the proton mass. So the typical up and down quark masses are a few MeV, and the proton is the GeV. And so you can see that actually the quark masses account for very little of the proton mass. And so where does the proton mass come from? Well, 99% of it, the rest of it, except for the quark masses, comes from the self-generating gluon field. It's actually the confining gluon field for the proton. And it's important to realize that actually the famous Higgs mechanism, which has been in the news a lot lately as the source of all mass in the universe, actually has, or all the visible universe, the Higgs mechanism has almost no role in this process. It generates the actual up and down quark masses, a few percent, but the gluons are the thing that generates the main bulk of the mass of the nucleon. It's also true, you can see this, that the similarity of the mass between the proton and the neutron arises from the fact that the gluon dynamics are the same. It's basically a ball of glue. And the quarks contribute very little. We now understand a lot about this now from combination of model calculations and lattice QCD calculations. And this shows a very interesting graph that's shown quite a bit these days. So you can actually calculate the effective quark mass, which is the term in the quark propagator, if you like, that looks like the mass, as a function of the quark momentum. So if you write out the propagator of a quark in a nucleon, you can actually write this quark mass term as a function of the momentum, and it's not a constant. At very high momenta, it's the value you put in for the essentially static mass of the quark, of the bare quark. But as the momentum is decreased, this quark sort of accretes mass by gluons seem to glom onto it, right? And it grows to be roughly a third of the proton mass. And so you can see that at very small quark momenta, you have this typical picture of three quarks that contain all of the proton mass, but actually the quarks only had a very small amount of bare quark mass of 30 MeV. And this dynamical effect is what's known as the dynamical breaking of chiral symmetry gives you this effect. And so these points on here with error bars are from the lattice calculations. And you can't do a lattice calculation yet in the chiral limit where the masses are zero, but you can see that you can take the same model that predicts, that reproduces these lattice calculations and predict what you would see for m equals 0, and you get the same picture is preserved. So we now seem to have a lot of understanding of the dynamics of how the gluons can explain the light quark dynamics in deep inelastic scattering, and also the simple quark model that we all learn as students. All right, so what are the science questions for Jefferson Lab in the 21st century as we go forward now? So one is, what is the role of the gluonic excitations in the spectroscopy of light mesons? And we'll cover this a little later, but the question is, can you actually see in the spectroscopy the effect of the degree of freedom of the gluons? And then can these excitations elucidate the origin of quark confinement, since the quark and antiquark wouldn't be confined if it weren't for those gluons? Where is the missing spin in the nucleon? As I told you, we're still having difficulty accounting for all of the spin in the nucleon, all the angular momentum. And what we can address at Jefferson Lab with the 12 GeV upgrade is whether there's a significant contribution from the valence quark orbital angular momentum. There's been a lot of work on new distribution functions to describe the nucleon beyond those one-dimensional parton distribution functions, and I'll talk about that. But the question is, can we reveal a novel landscape of nucleon substructure through measurements of these new multidimensional distribution functions? What is the relation between short-range nucleon-nucleon correlations, the partonic structure of nuclei, and the origin of the nuclear force? And can we discover evidence for physics beyond the standard model of particle physics? So we hope to be able to answer and address all of these questions. Let me give you a little tour of the facility before we talk about science, and I'll tell you a little about the technology as well. So here is an overview of the accelerator facility known as a Continuous Electron Beam Accelerator Facility, or STEBAF. Basically, you have a polarized electron source here. The electrons are injected into a superconducting linac that gives us roughly a half GeV of energy for each pass. Then there is a recirculating arc where the beam is bent around through another linac. And so you can then take the 1 GeV beam and send it to any of 3 experimental halls. Or you can take a fraction of the beam and send it around again through this arc into the same linac. You have to meet up at the same phase as the beam coming in, and be accelerated along with the beam, with actually has less energy, but they're all ultra-relativistic, so this actually works just fine. And they can come around again, and you have 2 GeV, and you can send 2 GeV to another Hall. And you can go around a total of 5 times to get 5 GeV, and actually if we push the gradient of the cavities up to as far as we've been able to do so far, they can get the beam up to 6 GeV. So that's the basic concept. It was very novel when it was proposed in the late 1980s. Facility came on in 1995 and has been running very productively since then, with energies between 4 and 6 GeV generally. But let me tell you, this is an overview photograph with a little bit of, cartoon drawings on it. Let me show you, take you for a tour since you're not there. If you go down in the accelerator tunnel, it looks like this, which looks a lot like any other accelerator tunnel you might have been in. But there are these big vacuum tanks that contain the superconducting radio frequency cavities, which are cooled by liquid helium at 2 degrees Kelvin. And here are the cavities being prepared before they're assembled inside these things called cryo modules. And so these are the cavities, and you can see that they have these elliptical shape, and they are built in these pairs and then put together in strings into these cryo modules. You can see it's all clean room operation because the preparation of the inner surface of these superconducting cavities is a very delicate situation. You need to have them very clean. They do chemical processing of the surfaces and so forth. Any tiny speck of dust or any imperfection can lead to field emission, which would limit the maximum gradient that the cavity can sustain. So there are 3 experimental halls, A, B, and C, and this shows you one of the early installations called the CBAF Large Acceptance Spectrometer class in Hall B that has done a lot of spectroscopy work. It's a superconducting toroid. It was a very novel device at the time. Actually still is, although it's being disassembled now in preparation for a completely new device that will replace it. That just gives you an example of the kind of instrumentation. There's a building over here that contains a facility known as a free electron laser. And this is a device where you take a high-intensity electron beam and put it through an undulator or wiggler, as they're known, and you can generate coherent beams of light. Lasers, and this is an infrared laser. It's capable of generating 14 kilowatts of infrared light. This is an operation that's funded by the Office of Naval Research, who believes this is fundamental R&D towards the development of future weapon systems capable of shooting down cruise missiles and such. But we have this device, and it's actually something you can, as you might imagine, do some interesting physics experiments or science experiments on. And I'll mention that a little bit later. And then there's a new experimental hall D. We're not very imaginative with new names, so, well, we don't have famous donors to name them after. Maybe that's the trick, huh? But there's a new experimental hall D here that we'll discuss in the future in a little bit as part of the upgraded facility. All right, so that's a tour of what we have. As I mentioned, to build this type of accelerator, you need to be able to construct and clean and process these superconducting cavities. And we have a very effective IT department as well. It likes to update my computer all the time. I do my best to resist, but eventually the computer stops working. Anyway, hopefully not in the next hour. So to prepare all of these cavities, we have a facility. This is actually an old cyclotron lab from NASA that the cyclotron's been gone a long time, called the Space Radiation Effects Laboratory. We're back, I think, in the 50s and 60s. They, probably the 60s, they were irradiating animals and so forth in preparation for spaceflight. And so you can see that here's an electron beam welder, which is what you need to fabricate those cavities. Here's the cleaning room where you do the buffered chemical polishing. They also do electropolishing sometimes. There's a variety of techniques that are used to clean these things. This is a vertical test facility where you can take one of those cavities and put it down into a hole in this concrete floor And this is shielding over the top because if you test these cavities, when you get field emission, the electrons get to several MeV of energy and even over 10 MeV of energy, and you can generate neutrons. And so there's actually a radiation hazard, and they have to be down in a concrete bunker. There's another place to test the full strings at lower power, and then there's you can see the strings are put together into these cryo modules in this area here. And it's really the only place in the world where you can take a piece of niobium and start fabricating it and end up with a production piece of accelerator hardware. And so it's really pretty unique that way. And it's really very important for R&D in developing new cavities and new configurations. This has all been, when there was the Recovery Act a few years ago, the Department of Energy received some money associated with improving infrastructure at the laboratories. And so we got a new building added on to this, and so it's really a nice upgraded, this is a recent picture, nice upgraded facility. The old cyclotron building is there. And so we actually have quite an enhanced capability for doing this kind of work. Of course, we're mostly completed with building the new cavities for the upgrade. That's one of the things that's kept us busy recently. But there's a lot of work still coming down the pipe that we think will be useful for our facility. One is the facility for rare isotope beams at Michigan State, where we are contributing to the cryogenic system that they will need. They also have a superconducting LINAC as part of their new facility, and we are hoping to play a big role in their cavity production as well. What I maybe should have pointed out on the previous slide is there's something called the Spallation neutron source at Oak Ridge National Laboratory, which is roughly a GeV proton accelerator, high-intensity proton accelerator. We constructed the complete superconducting accelerator and in pieces in these cryo modules, bagged them up, sent them over to Oak Ridge. They were all assembled, and it's now a completely functioning accelerator. So the lab has a history of building these accelerators and can deliver a complete system to people. There's something at Fermilab called Project X, and we helped them design a new cavity, and we've been working on constructing a prototype. There's something called the European Spallation source, the European version of this SNS at Oak Ridge, and we're negotiating with them on possibly helping them with their cavities as well. And there's something that presumably will be built at Berkeley called the Next Generation Light Source, which is not a synchrotron, but is based on a superconducting LINAC technology, which is a collaboration of several labs, and we're one of the important collaborators for that as well. So there's a lot of work to do in this SRF business, and we're kind of in the middle of it, and certainly one of the leading labs in the world on it. This shows a recent result they got. There's a lot of information on here, but basically they took niobium that didn't pass any of the purity specs that they would normally apply and treated it a new way using a heat treating furnace, a UHV furnace, that again was funded by recovery money. And you can see that this is the Q value as a function of basically the field in the cavity. And this is significantly higher, about a factor of 2.5 higher than they've ever seen before under these conditions. And so, again, A, it's a very empirical process, and B, you can see that by people trying out different techniques based on, not based on solid theory, but based on some understanding of the properties of the surface, they're actually able to make progress on improving the Q and the gradients that can be sustained in these cavities. So here's basically what our upgrade project is about. This was something in the Nuclear Science Advisory Committee in 2007, and their long-range plan, ranked as their highest priority, was the completion of this upgrade project. And as you'll see, we're about 70% of the way through right now. Let me tell you what the idea was. So there's an interesting story to begin with, is that there was empty space in the accelerator tunnels that was left from the original construction. Now that seems like we didn't design this properly, but what actually happened was the original design was for 4 recirculations instead of 5. and that there would be more superconducting RF cavities. So you just accelerate more on each turn and do 4 recirculations. Well, once they got close to construction and they actually knew what the real costs were of building all these various components, you could do a new calculation, and the trade-off that was favorable would cost less and actually give better performance, it was found, was to build less superconducting RF, but do 5 recirculations. Of course, the civil construction had already been laid out and started, so you couldn't shrink the size of the facility, so there was empty space in the tunnels. So now, here we are 20 years later, and the properties of these cavities have improved so much that they have roughly 4 times the performance of the previous ones. So you can replace these 20 cryo modules, or you can add to these 20 cryo modules 5 new cryo modules and double the energy. Okay, so basically the gradient is factor of 4 higher. So that was the plan. It's a very cost-effective use of the existing infrastructure. And of course, to keep all that stuff cold, you have to upgrade the central helium liquefier. Then, of course, the beams are higher energy in the arcs, so you need to upgrade the magnets and the power supplies for the arcs. And in addition, of course, you want to have better experimental equipment that would handle the 12 GeV beams and give you new capabilities. And so that was part of the project as well. So now you can see we can do 2.2 GeV on each pass. And actually, we get 11 GeV in each of these halls. And you can go around one more time and get another GeV here to go to a new experimental hall, Hall D, which is the only one that actually gets 12 GeV beam. So that's the idea of the upgrade project. The physics program, I've talked about the questions, so I don't think I'm going to go through the details of this. We'll actually talk some more as we go through the remainder of this presentation. But we've had 8 reviews at our program advisory committee. There are 52 experiments approved, 15 conditionally approved that have some additional features that need to be worked out before the committee gives full approval. And we have a white paper for Bob Tribble's NSAC subcommittee that actually, this is an old slide, it's finished, and we gave it to them. But there are enough experiments for all 4 of these holes that would keep us operating for about 7 years of full-time operation beginning in FY15. So this takes us out to 2022 or so, roughly 10 years from now. So there's quite a bit of stuff on the books, and we hold a new committee meeting every year, and people bring in new ideas. And so we haven't scheduled out all of that time. We can still schedule things as we like, and we might change the priorities as we go along, but that's the present status of the program. Just to give you an idea, here are the 4 halls and the different physics topics, and you can see kind of how things are distributed in terms of numbers of experiments. A little more relevant is the number of what's called packed days approved for each of the halls, and you can see how that works out. And this, from this total 3,000, and the fact that you can only run so many halls at a time, roughly 2.5 or 3, is how you end up with more than 7 years of approved experiments. So what are the scientific capabilities based on, we know, I gave you some questions that we'd like to answer. What does the equipment look like that we need to address those questions? So to address this question of confinement and the exotic mesons, we have the Gluex experiment, which is the experiment in Hall D, which is a completely new installation for us. Jeez. Getting more insistent. And and I'll tell you how that experiment works. Hall B, which had this large acceptance spectrometer, all of that's being removed, and we're building a completely new large acceptance spectrometer. And this is optimized for measuring nucleon structure via new things called generalized parton distributions, which I'll tell you about. Hall C has these, can study these valence quark distributions at higher values of X, and also precision measurements that give you information on those properties in nucleons as well as nuclei. There's a new spectrometer being built for Hall C. Hall A will continue with form factors, but is the place where we're going to build future new experiments, and I'll tell you something about those as we go along as well. So these new experiments beyond the 12 GeV upgrade are shown here. We've already, of course, since 2007, people have thought of lots of new things to do. And we have some new programs that we're starting at the lab that we've been talking to the Department of Energy about. One that we pretty much are all set to start, in fact, it starts construction this month, is something called Super Big Byte Spectrometer. These all go in Hall A, by the way, where there was no new equipment from the project. This is the, then there's a Muller experiment for parity violating electron-electron scattering, which is a test of the standard model. This is what DOE calls a major instrumentation. I can't remember what MIE is now. Equipment, major item of equipment. That's what it is. And then solid is the solenoidal large intensity device, which is a big solenoid. We're thinking of getting the Clio solenoid, although maybe the Babar solenoid from SLAC will become available. We have a fairly substantial Chinese collaboration on that. So even though we have this $310 million upgrade project in progress, 70% complete, we've got a series of new projects that we think will utilize that facility down the line over the next decade or so. So here's the schedule for the project. When you have a project with DOE, you have to have a schedule. And the vertical line here shows where we are. We're actually, our accelerator is shut down. We shut down on May 18th. And this shutdown used to be a 12-month shutdown, but it's now a 16-month shutdown. And the reason is that in FY12, which just ended, we received $16 million less than the project schedule called for. And so we had to stretch out this installation work, and some of these other things will be delayed slightly. And there's a question of really whether we're going to make the final completion date as originally envisioned. All of that, of course, depends on when and how that $16 million comes back and whatever else comes to us, how else, the funding profile emerges over the next year or two. And so there's a review at the end of November to really assess and what they call rebaseline the project, to set up a new cost and schedule for the project. And this just gives you some pictures. Here's Hall D, which is now mostly complete. In fact, it looks better than that now. They've essentially completed these central drift chambers for Hall D. This shows the arc magnets installed. That's been done. Some of the cryo modules have already been installed and tested. I'll show you a test result, I think. I left it in this presentation. So you can see there's lots of hardware has already been done. Here is in Hall D is a superconducting magnet. Bob Tribble may recognize it as the previous magnet used at Los Alamos for an experiment called MEGA. These are the cryo modules being transferred into the tunnel. Here's the central helium liquefier, huge refrigeration system, lots of detector construction going along. And so it's really going quite well. So, Hall D, how is this experiment going to work? And here's the basic idea. So we take the 12 GeV electron beam. It's incident on a very thin diamond wafer. It's carefully aligned. And so you get coherent bremsstrahlung. So you get bremsstrahlung, but it's coherent from the different atoms or different nuclei in the diamond wafer. And so you get a very intense beam with a very narrow angular width, and it's quasi-monochromatic, around 9 GeV. The electron is bent by a magnet and then detected in an array of detectors. And by measuring the energy of that electron and doing a coincidence with the event from the photon, you can actually determine what the energy of that photon was more precisely, to a few percent. Then you have this, this is the Gluex spectrometer, which has the superconducting solenoid. You can see there's lots of tracking chambers and barrel calorimeters. There's a calorimeter in the forward direction. And the idea of the experiment is that you make this photon beam. The photon fluctuates into a quark-antiquark pair, interacts with the nucleon in the target shown here, and excites the gluon field between the Q bar pair and makes what's called an exotic meson, a meson that has quantum numbers that are not available to just a Q bar pair. And then this meson will decay into 3, 4, 5 particles, 3, 4, 5 other mesons, and you need to detect them all and do what's called a partial wave analysis and try to determine whether there are particles with these exotic quantum numbers in the spectrum of the things that are produced. So this just shows what I said in words, that you can take QQ bar and spin singlet, spin triplet. You can add excited gluon field and get these what are called hybrid mesons, which have these quantum numbers. And there are these combinations for the triplet QQ bar pair that are exotic, that are not, you can't get these quantum numbers with simply a QQ bar pair. And so those are the particular quantum numbers that experimentalists will be looking for. There's been a lot of progress in the Lattice Qcd calculations. Lattice Qcd calculations, as I alluded to before, are done as a function of the pion mass, or equivalently the quark masses. And the idea is to try to extrapolate to the physical limit, which is close to this axis here. And using these using these graphical processor units at JLab, our theory group has been able to generate these points with very small error bars. These are unquenched calculations with dynamical fermions. And you can see that first of all, it's a major improvement over the previous calculations. And secondly, that the masses of these objects are being predicted to be right in the 2 to 2.5 GeV mass range that would be accessible by the Gluex experiment. So things are looking much more promising than even a few years ago, that this experiment will give new discoveries for these exotic mesons. Oh, this is a nice graph of using these graphical processor units. So if you look at megaflops per dollar as a function of year, our group, with some stimulus money, was able to purchase graphical processor units instead of CPUs that they originally proposed, and jumped off the cost performance curve here in a nice way. So, and I think this is something that's being adopted not only elsewhere in Lattice QCD, but in many areas of computational science these days. So coming back to the nucleon, there's this, I mentioned the spin puzzle before. It was, where does the spin of the nucleon come from in terms of its constituents? This is something that's been worked on now for more than 20 years. And you can see that this is some rule due to Zhengdong Ji in 1997. We were able to show that the spin of the nucleon should come from the helicities of the quarks, the angular momentum of the quarks, and the orbital angular momentum of the quarks, and the angular momentum in the gluons. And this has been known for some time. This has been known as the nucleon spin puzzle, that this delta sigma, which is the quark helicity contribution, is only a quarter of the total amount. So sort of 3/4 of the spin of the nucleon has been unaccounted for. Particularly experiments at RIC, but coupled with deep inelastic scattering experiments, attempted to find the gluon contribution. And here it's shown that so far the gluon contribution seems to also be a small fraction, although I understand recent data from RIC indicates that maybe it's non-zero. And so we're looking forward to a release of those results soon, hopefully. But there's a lot of interest in the orbital angular momentum of the quarks as a result, is that maybe this is a significant part of the answer. And there are calculations that show how you can access this using new distribution functions that I'd like to discuss. So this leads to something called a unified view of nucleon structure. And really sorry about this. I guess I'm going to have to deal with that soon. Okay, so I've shown you this in a different scale before, but these are the usual one-dimensional parton distribution functions. And I want to remind you how we got there, okay? There were these deep inelastic scattering experiments at SLAC. They showed the scaling property. People like Bjorkane and Feynman realized that this could be understood in terms of these point-like constituents. And in particular, Feynman had this view that, well, okay, you want to get rid of, you don't want to worry about the masses of these constituents, and you don't want to worry about their transverse momentum. So what we'll do is we'll look at them in an infinite momentum frame. And so basically the transverse momentum is gone and the masses are irrelevant. and all you have are ultra-relativistic particles coming at you at the speed of light. Now, if you're interested in, say, orbital angular momentum, you realize that you would need to have transverse momentum of those partons in order to generate the orbital angular momentum. So what you've done is create a calculation or a model that nicely reproduces these data, these one-dimensional parton distribution functions. But if you're really interested in how the quarks are orbiting to generate orbital angular momentum, you've basically thrown out the baby with the bathwater. It's gone, right? So it's a very nice description. But if you're trying to, if you're trying to understand where does all the spin of the nucleon come from, it's not in this picture, and that's one of the problems. Similarly, if you look at the usual elastic form factor, these are also one-dimensional distributions. All these distributions may somehow be affected by the presence of, say, orbital angular momentum, but there are no, in a one-dimensional distribution, it's very simple to understand as a physicist that you can't get an orbital angular momentum signature out of it. So these are one-dimensional distributions, which are a problem. We'd like to do more than that. So to do more than that, we can go all the way back to the beginning, and you can basically describe the nucleon in terms of these Wigner distributions, which are functions of six-dimensional phase space, momentum, and position. And that's too much to measure. So we integrate away some of those variables, and we can get these generalized parton distributions. And those generalized parton distributions, if you integrate more variables away, can reproduce these parton distribution functions or these elastic form factors. So these are really great things to be able to try to measure. There are also transverse momentum distributions as another path where you integrate away the spatial degrees of freedom. And then you have, again, you can get the PDFs. And so the idea is now to study these GPDs or these TMDs, transverse momentum distributions or generalized parton distributions. And these, you can see by these pictures, have features of orbital angular momentum that allow you to access those things, and you can get information on that. This shows you that there are actually 4 of these generalized parton distributions. I don't really have time to go through these, but by measuring polarized beam and polarized targets, you can access these different distributions in deeply virtual Compton scattering. And there's a sum rule due to G, where if you could measure H and E and perform this integral, which you probably can't fully do experimentally, but this would be the goal, you could actually get the total angular momentum carried by that flavor of quark. And there have been analyses of some of recent data using models that seem to indicate that this is a reasonable program to pursue in the future. And so the new experiment, class 12, will get very detailed information over all these kinematics and be able to give you this imaging as a function of X Bjorkane, transverse distribution of each of the flavors of quarks. Lots of information that we don't have now. The transverse momentum distributions, there are actually 8 of them that can be measured in semi-inclusive deep inelastic scattering, where you detect a hadron in addition to the scattered electron. In SLAC, they only measure the scattered electron, for example. Again, you can do an imaging of the nucleon using this technology. All of these different complementary pieces of equipment can address these questions. And then I want to talk in the remainder of the time a little bit about parity violation. So we've been working with parity violating electron scattering for some time. This is an experiment I worked on at Jefferson Lab called G0. The idea is that these gluons, of course, generate quark-antiquark pairs, and they should generate strange quark-antiquark pairs. This is quite analogous to the Lamb shift in atoms, and these strange quark-antiquark pairs in principle can contribute to the proton's magnetism, the magnetic moment. You can study it using very small, few parts per million left-right difference in the electron-proton force by doing parity violating electron scattering. So these are very challenging experiments, and there's been a whole program of these things at JLab. I'm not going to go through the details, but basically you measure a product of photon exchange and Z exchange to access these Z exchange form factors, which give you the new information. There's been a variety of experiments that have been done. This is the most recent graph. It shows, here's the most precise measurement. These two are the most precise measurements that have been done at JLab. And actually, it's been very surprising that the strange quarks do not appear in these form factors. All of the measurements are essentially consistent with zero. We thought for a while that these might be non-zero, but these new, more precise points really indicate that probably everything looks like as close to zero as we can measure. So what else can you do with parity violating electron scattering? I want to give you a little insight into that, what's coming down the pipe. So if you look at the weak charge of the proton, the electric charge of the proton is 1. The electric charge of the neutron is 0. We all know that. But the weak charge of the proton goes as 1 minus 4 sine squared of the weak mixing angle, which is close to a quarter. So this number is actually quite small. The weak charge of the neutron is minus 1. So if you measure the Z coupling to a nucleus, you'll pick out the neutrons preferentially over the protons. And so if you do parity violating electron scattering from a heavy nucleus like lead, this will be sensitive to the distribution of neutrons, which is very hard to measure in a model independent way. And, so this is something that's of great interest. The applications are that not only is it interesting to nuclear physics, something called the symmetry equation of state, but this affects the structure of neutron stars, for example, and is relevant for other experiments in heavy ion collisions and so forth. And so this shows you what we think we can do. The previous experiment that was run at Jefferson Lab gave this result for the neutron-proton radius difference in lead. And these are two different effective interactions. The new measurement that's being proposed, it'll probably run in a couple of years, is shown here, and should give a pretty definitive answer on this neutron skin in lead. Another subject is the running of the weak coupling constant. So this sine squared theta W is not a constant, but varies as a function of momentum scale. It's very tightly constrained at the Z mass by the data from high energy experiments. But it's interesting to see this running, and you can see that the combination of these data points seems to indicate that the coupling constant is changing with momentum scale. And so we have a new experiment that just finished called Q-weak that measures the weak charge of the proton. Again, here's this expression so you can see how it's sensitive to theta W. There's a future experiment in electron-electron scattering that we hope to build, shown here. And then there, as I mentioned, there's this solid experiment that also can access parity violating deep electron quark scattering. And so what we hope in the future would be the situation is that here is this running predicted from theory. Actually, the width of this line is what the theorists think the uncertainty is. And these are the projected new points from Jefferson Lab, and I think you can see that would be a very substantial advance in our knowledge of the running of this coupling constant. Of course, if the data points do not follow this curve, there's an indication that there are some other particles in the loops and so forth in the calculations of the radiative corrections. And so as a way of discovering new particles, it's very complementary to high energy experiments like the Large Hadron Collider. So finally, before I finish, let me mention dark matter. I think most people are familiar with this, these colliding galactic clusters called the bullet cluster, where it appears that the baryonic matter is separated from the dark matter. We now know from many experiments that dark matter is 26% of the matter of the energy density of the universe, and dark energy is 70%, baryons being the remainder, 4%. So the dark sector energy and matter is new physics beyond the standard model. There are many direct searches for dark matter that maybe you've heard about with sensitive detectors, and there are hints but no established signal yet. And there's controversial evidence for excess astrophysical positrons, and let me show you what that looks like. Here are data from a satellite experiment called Pamela, where they measure the positron fraction relative to electrons plus positrons as a function of energy. And relative to what was previously expected in astrophysical models of productions of energetic electrons and positrons, you see this dramatic rise of the positron fraction where it's up above 10% and still going up. This is very different from p-bars compared to p's. So p-bars are down around 10 to the minus 4, and they're not changing in this dramatic way. The positrons are. And recent data from the Fermi satellite also confirm this rise. This is the previous data from Pamela, and you can see it's even stronger evidence for this rise of the positron fraction. So it seems like a real effect. One way you could generate this is if there's dark matter that annihilates into particles called dark photons, which have a mass less than 1 GeV, so they can't make proton-antiproton pairs, but can make electron-positron pairs, maybe muon pairs, but certainly electron-positron pairs. You could generate an excess of positrons, and this is a popular model for explaining this phenomenon. But you can never rule out the fact that some clever theoretical astrophysicists will come up with a way for generating positrons. So nevertheless, there's some motivation for looking for these dark photons and evidence for them. I should point out that there's also the Brookhaven G-2 experiment for the muon, where the anomalous moment of the muon has been measured and deviates from the standard model prediction by about 3.5 sigma. And remind you that this was something that was thought would be evidence for supersymmetry, but there's no evidence for supersymmetry at LHC yet. And this A prime would also be another way of explaining this phenomenon of G-2 observation. And as I pointed out, it's also useful for dark matter models. So how you can detect the presence of this, the existence of this A prime is you take an intense electron beam, for example, at Jefferson lab, and scatter from a nucleus or a nucleon, and you can, through sort of a Bremsstrahlung process, create this A prime instead of a photon, and this A prime would decay into electron-positron pairs. Now, of course, this diagram with a photon here also exists, and but it would generate a continuum of electron-positron pairs. If you plot the mass distribution of these pairs, the existence of the A prime would show up as a very narrow spike. So we actually have 3 proposals for looking for these A primes in 2 holes and 1 at the free electron laser. And this shows the situation where the gray areas are already ruled out by a variety of other experiments. This green band is what's favored by this Brookhaven G-2 experiment. And then the new experiments at Jefferson Lab would completely cover this region here and also this island shown below. And so we're hoping to pursue this program when the beam comes on in the future. So that's another new thing that's come up at the lab. So this just shows you the potential. I think I've been through these. I want to move on and finish up with a brief treatment of this electron-ion collider, which in 2007 was identified as a new opportunity for the field of nuclear physics. Brookhaven and Jefferson Lab are both working on designs for such a project. The basic idea is the following. You're now familiar with these parton distribution functions. The 12 GeV project will address the valence quark distributions. But of course, if you go to much higher center of mass energies, you can continue to study the same type of phenomena, all of these new distribution functions and so forth, into the region where the gluons are dominating the dynamics and hopefully discover new phenomena. So that's the basic plan, and here's kind of a cartoon of doing these transverse images right down into the region where the radiative gluons are dominating. This is a picture, a diagram of our proposed design. It's very novel. It has this figure 8 colliding ring design, and the idea is that this is a way of overcoming the depolarization of the particles of the ion beams as you accelerate them using this figure 8 design. And this shows you roughly how it would fit on our site. We think that that's kind of the future, and that, for example, if the nuclear physics community continues to build FRIB through the end of the decade, that would be a time when you could start construction of such a new project. So I'll bring you back to our laboratory and just conclude with the outlook that We're a unique world-leading facility for nuclear physics research. The upgrade ensures a decade of excellent opportunities, QCD beyond the standard model, and the additional equipment we need to pursue these programs shown here. The Collider project is something that we see moving forward. There's a strong science case. Much of it builds on what we're doing with the 12 GeV program. And the design is actually fairly well developed, and that a timescale following the 12 GeV program is quite natural for our laboratory. So we're hopeful that that's actually what's in our future. Thanks very much for your attention. Right. Yes, there are, and it's you know, the number that you detect is kind of a difficult quantity to present, because you need to do this partial wave analysis. So there are many events, and so what the Gluex collaboration does is take a typical model that generates these particles at the rates they expect. And they haven't been seen before because there's never been a photon beam that would allow you to do this. And the idea of that cartoon I showed you is that starting with S equals 1, spin triplet quarks, which you get from a photon fluctuating into a row, is a good way to do it. It's favorable, as opposed to using a pion beam, which is what's been done in the past. And and then what they do is they take that predicted rate, they divide it by 100, so it's tiny, and then they throw it together with all the other known processes and backgrounds and so forth, and do a simulation, and then do a partial wave analysis and try to extract this signal, and it pops up. I don't have the slide here, it just pops right up. So I think they expect that even in a year or two of running, that even if it's a factor of 100 below what you might naively predict, they should be able to find it. That being said, I think the history of partial wave analysis in Baryon and Meson spectroscopy has been a difficult one, and there have been false signals and difficulties all along, as you may know. So I think one has to treat the subject with some skepticism, and but nevertheless, based on what people have reasonably been able to predict, it looks really quite favorable. But these are not first principles calculations. I have to admit.
Yeah. So a similar question on a different experiment. So some of these reactions that you study, for example, for the generalized Baryon distributions, are rather rare. So luminosity is important. I didn't really explain about what the upgrade has in stock for the luminosity, and how long would it take to measure one of these some of these generalized Baryon distributions to some kind of satisfying accuracy.
Right. So I took that one example from class 12 and showed you the projected data and so forth, and that's for one combination with a longitudinally polarized beam and unpolarized target, and that's the most favorable for getting H, generalized part-time distribution. And I think that takes a good fraction of a year of running, typically. And then there are the other three combinations of polarized target, unpolarized beam, polarized target, and then unpolarized. Equivalent amount of running for all of those. So I think the total program represents probably 4 years of flat-out running with that class 12 device. So it's and it's difficult. The reason is, of course, in deeply virtual Compton scattering, you've got two photons. So you got electron scattering is hard enough. Now you get another alpha. So as you pointed out, getting the events is difficult. But the large acceptance and the large luminosity.
Here's the program of getting the spectral function. But I remember when we start talking about CBAF, one of the shortest words.
Yeah, the spectral function of the nucleons is something for nucleons in a nucleus. Yeah. So this is something that's been studied for quite some time, and I think where the subject has moved on to is to look at these short-range correlations, you know, and the 2-nucleon and 3-nucleon effects. But the single nucleon spectral function, I don't think there aren't proposals really to move that subject further than it is. I think we have a lot of information on that. It's something that the neutrino physicists, for example, should learn to use. They still describe a nucleus as a Fermi gas and then claim they're confused about their cross sections. And I interact with these people a lot, and it's kind of a problem to get them to use real nuclear physics, these spectral functions, which have been measured in detail in previous experiments. But you also need meson exchange current effects and correlations and so forth to describe a real nucleus. And I think that even the neutrino experimentalists are starting to appreciate that as well, as they talk to more nuclear theorists who know that that's what you need to do to describe electron scattering data. It's not going to be any easier to describe neutrino scattering data. So it's an important issue. But I don't think it's something that, in terms of trying to explore the spectral functions further, that we're doing now at Jefferson Lab. What is being done is at very large x, beyond x of 2 or 3, trying to study the correlations of 2-nucleon, 3-nucleon, 4-nucleon correlations in deep inelastic scattering is something that is still being pursued.
Any other questions? Okay, well, no, thanks very much, Bob.
Okay, thank you.